Welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we're doing physical science. And we're going to talk about waves, electricity, and magnetism. So this is our last standard for our physical science class. And these notes you may use on the test. And it's going to come straight off of the notes. So this is your cheat sheet for the test. So write them down. All right, there's two kinds of waves. The first kind is like a slinky when you go it makes that noise, right? And the second one, and so that kind of wave our example is sound. This is the kind of wave that sound is. So don't let me write now. It's not letting me write, Ms. Olivier.
I can't help you with that. I don't
okay,
know
now.
how to do that.
It's writing. It's not making a black line around it either. Example of sound, and sound is made by what's big E in science?
Energy.
Energy, right. So sound's made by energy. How often the compressions come is called the frequency. It's how often the compressions or the waves come. And the units of frequency is called hertz. Hertz. Okay, our second kind of wave is called a transverse wave. It's like the wave in the ocean. Transverse. So here's our transverse wave. The little tops of the waves are called the crest. And we call them that in just regular English, don't we? If you're going surfing, you catch the crest of the wave. The bottom parts are called the trough. Like a pig trough, the pig would eat out of. So that's just a regular English word too. The measurement from crest to crest or trough to trough is called the wavelength. That makes sense. That's nothing fancy, is it? But the symbol for it is a Greek letter. It looks like a little upside down Y. And that's the symbol for wavelength. It's sort of like a little teepee kind of thing or an upside down Y. The height of the wave is the amplitude. And you're familiar with that if you know about sound equipment and you have an amp for your stereo. It makes the waves taller, and those electrical waves would be changed to louder sound, right? So one of the formulas we have for wavelength is it's speed over frequency. This little V stands for velocity, but it's really a speed. I feel like scientists, I know this will shock you, are kind of nerds, and they try to use fancy words when a plain word would do. Excuse me. It's really speed there, it's not velocity. Excuse me. Velocity is speed with direction. And there is no direction on this. It's just a speed. Okay? Next idea. Waves can bounce off. They can bounce back, and that's called they can be reflected. That's another regular English word, right? If a wave came up and it bounced off your boat, it would make sense to you that that wave had been reflected. They can also be just not bounced straight back, but just sort of bent how it goes, and that's called refracted. R-E-F-R-A-C-T-E-D. Reflected or refracted, which changes direction. Waves can also spread out. That's called diffraction. One F or two F. Can be diffracted, or they can run into each other. When they run into each other, it's called interference. That's a regular word too, isn't it? Now, I didn't know how to draw this, so I'm just going to sort of show it to you. If you have two waves coming along, they're both going up like this. When they run into each other, and what they do is they get doubly tall. So if you have one wave coming along and another one, they stand on top of each other and get doubly tall. If you have a wave going a trough coming along and another one and they run into each other, they get doubly deep. If you have one wave going a trough and one a wave and they run into each other, they'll flatten out and then they'll keep going their merry way. So that's how interference works. Waves can, so they can interfere. And we know that with even like electricity. Like you can have interference where you're getting feedback with electricity. And then I put that little cartoon at the bottom because it was funny and it had waves. It had nothing to do with the notes, except poor little Duncan is flying off the pier. Okay, can we scroll? We get on this page? See, I told you it's a lot of pages, but it's not a whole lot of information. Oh, it's going to be bad. Why am I not surprised it's going to be bad?
Ms. Blackburn, what is the next test?
It's probably going to be on Monday. We'll work on these notes today and tomorrow, and then we'll have our open note test on Monday. I guess it doesn't matter. Okay, more about sound is the next page. But look how it's got that there. I wonder if I can erase those. Let's try that. Let's try erasing. Nope. All right, we'll see if he'll let us write. It's acting bad. But we got one page done of this big fat packet, the front page of it.
Good.
Turn to the back.
Good.
More about sound. Okay, things that stop sound are called insulators. Hey, it's let me write. Insulators. Just like how insulators can stop heat moving, the same insulators can stop sound moving. So there are careers you can go into where you help design sound for places to either be loud or quiet. Like you go to a concert hall, they will design the sound so everybody can hear in the audience. You can get a degree in sound design. That's pretty interesting. Now, which one do you think can transmit sound the fastest? Which one are you going to be able to hear sound the quickest through? Solid, liquid, or gas? What do y'all think? It's solid. To me, it seems weird, but how you can tell this is solid is the fastest, liquid is in the middle, and air is the slowest. And how you know this is if you've ever swum in a lake. You ever went swimming in a lake, and you're swimming in the lake, and it's silent. You just hear the birds. You go under the water and you can hear a boat that's far, far away. And then you come back up thinking, I'm about to get hit by the boat. And there is no boat. You're hearing it far away. And then the other thing, you see it in movies, but don't do it. In movies, you will see, especially like old Westerns, they want to know if the train is coming. and they'll listen with their ear in the air and they don't hear the train. And then they'll put their ear on the railroad track and they can hear the train coming because the sound is traveling best through those railroad tracks. Now, never in real life put your head on a railroad track. I don't want your head getting squished like a melon. No getting run over by a train. When I used to live in Douglasville a long time ago, there was a little boy who bought Pokemon cards. And he was so excited and was looking at them and was walking along and not looking where he was going. And he got hit and killed by the train in downtown Douglasville. It just broke my heart that he wasn't paying attention. So always pay attention around trains. Don't let one hit you. Okay, so which one next can transmit out the sound fastest? It's the solid. Now, how high a sound is, what do we call that? Oh, that's a high, what's the word? Starts with a P. Pitch. Guadalupe knew it. Pitch is how high a sound is. And it's related to the length of whatever's making the sound. So someone who has a deep voice has long vocal cords. Someone who can sing real high has little short vocal cords. So if you have a rubber band and you pull it out long and pluck it, it goes boom, boom, boom. But you make it short, it goes tink, tink, tink. So pitch is related to length. Now, how is sound measured? If it's loud or soft, it's measured in decibels. Have y'all heard that word before? DECIBELS in decibels. So there's my guitar, or my banjo, and how you change the pitch is by pressing down on the strings to make them vibrate at different lengths. And that's how musical instruments work. Now, that's my cheerleading megaphone. Do our cheerleaders have megaphones, Miss Olivia?
Varsity football does.
Varsity football. When I was a college basketball cheerleader, we didn't have megaphones, but we had it when I cheered football in high school.
There's not really room on the side of the court.
No, and what are you going to do with them? Okay, so here's my little cheerleader megaphone, and this is about making sound bigger, and that's called to amplify. I bet y'all could just take this test right now and make 100 on it, because these are things that's all such common sense words you already know. So to amplify is to make this sound louder. What do we call unwanted sound? What do we call that? Oh, stop making that noise. Noise is unwanted sound. And so wanted sound, sort of on the other side, is music. And it's sometimes a debate, which is which, isn't it? Like I think Yoko Ono makes noise, not music. John Lennon's wife. It's not music, it's just noise. But other people love her music and say it's music, not noise. But if it's unwanted, we call it noise. Okay? So versus music. Now, music is very complicated. You can do whole classes on music theory, and you can learn about chords and about all the math of that even, and how sound can be induced from other things and resonance and all that. But we're not going all that. If you want to know more about music, you're going to have to learn that somewhere else. But I do want you to know that the musical scale is based on the number, do you know? It's number 8. Have you heard of octaves? Octaves, oct means 8 in Latin. So music, in the Western music, now I think Eastern music, like Japanese music, is different. But Western music is based on the number 8. So it's in octaves. The musical scale is in octaves. All right, Miss Olivier, let's see if we can scroll.
You ready?
I'm feeling good about it. Click on it some.
Click, click.
But it's not making red dots.
No, so is that good?
It's probably bad. See if you could click it. Oh, now there's some dots. Okay, and it's
no.
well, it's scrolling.
Wait a minute. It was moving the words up.
Yeah, but maybe we can just get to the blanks.
What do I do?
Exit out and try to open a new version of it.
Close it.
Yeah, close it and it'll say, well, sometimes it says, do you want to
It
say?
didn't do anything.
It didn't do anything. Try to reopen it, see if it'll reopen. No. Try to reopen the other one, the original, because that was where we saved it to A. If we have to, I could not write on it, and I could just tell y'all what to write. So we already did all this.
What's that doing?
It's just bouncing around. We are down to the railroad train. Okay, let's just talk about what goes in those blanks of the railroad train, okay? And y'all can write them down. And I'll point to it on here. And I'll write it over there. How about that? Let's do it that way. So the next thing is, see my train. And I think a better example of this is a motorcycle. But I couldn't draw a motorcycle, and I could draw a train. It seemed easier to me, okay? So so we're going to talk about a motorcycle, even though it's a picture of a train. Because the train was in the book. Okay, so you're outside your house, and there's a motorcycle going down the street, and you hear the motorcycle coming. What happened to the pitch as the motorcycle goes by me? What does it do? It shifts. It goes lower. That has a fancy name that you've heard on the weather called the Doppler Effect. The Doppler Effect. And I'll explain it to you. I need a marker, not this one that writes on the board so I can spell it. So underneath the train, write Doppler Effect.
On these two lines.
Uh-huh.
Doppler and effect.
And effect. And I'm writing down the board too. Doppler Effect. And it's used to predict weather. That's our other blank. Okay, and what it is, and you need to draw this on your train. Okay, so here's a little train. And see the person. Here's my little person. As the train is coming, the sound waves are being pushed close together. But as the train goes on by, you might have to draw another one, the sound waves spread out. So as something is moving and making sound and it's coming towards you, it has a higher pitch because look at this. How in the world are you doing this?
I have no idea.
It's used to predict weather.
I don't know if I could do it again, but...
You're doing awesome. Okay, so draw these little sound waves here, and they're real close in front of the train. But behind the train, they get real spread out. And so as the train, because the train's moving, it shoves the sound waves close here, and it makes them high-pitched. It spreads them out back here and makes them high-pitched and low-pitched. Does that make sense a little bit? They use it with the weather because they use it to look at clouds. And if the cloud is moving, it does the same thing with the light instead of sound. It makes the light red shifted or blue shifted. And why do we care in Georgia if clouds are turning or not? Tornadoes. We're one of the big tornado places. We have a lot of tornadoes here. So we care about if a cloud is rotating. That's bad news. Rotation. If you've ever seen those documentaries or if you've seen that movie Tornado, you don't want rotation. You want that cloud to just sit there and rain and not start turning and causing the Doppler effect. So you always hear about in the news, Doppler radar, and that's what they're looking for is how these clouds are moving. Can you make it scroll again?
I don't know. I'm on PDF right now.
Oh,
And it's working.
it's working. We're not going to curse it. Okay, next page. See how we're just blowing through these real fast? Properties of light. Now, this one was hard for me to learn. I had physical science in 9th grade when I was concussed, and I had such a hard time with this. Okay, and y'all are going to go, you're stupid. Well, no, I was brain damaged, actually, at that time. Okay, so these three words, transparent, opaque, and translucent. Transparent means that the light all comes through. You can see through it. Transparent. The light is transmitted. This is the one that was hard for me. If no light goes through, what is that called? Do y'all know the word? Opaque. Y'all are so smart. Now, I didn't know this, and this was the problem. O-P-A-Q-U-E. It was because it was the 80s. And in the 80s, girls wore pantyhose. And when you bought pantyhose at Macy's, you went and got your pantyhose, they would say they were opaque, but you could still see light through them. They weren't like a pair of leggings or tights. They were dark, but you could still see light through them. So I didn't understand that opaque means no light. A book is opaque. It does not let light through it. And it was because they mislabeled pantyhose, and I was concussed, and I would try so hard to remember it, and I never could, and I kept getting this one wrong. So transparent, you can see through it. Opaque, you can't. But what if you can see through it a little bit? It's called translucent. Y'all know these words already? Translucent. See, I really think y'all are just going to be ready for this test in a hurry here. Translucent, that's a terrible N. Okay, some light passes through. Now what about mirrors? What is it called what you see in a mirror? It starts with the letter I. You see your image. You see your image. The image is what you see in the mirror. And on Tuesday, you were supposed to do a little digital day where you played with this little electronic simulator of lenses and mirrors. So if you didn't do that, I'll run off copies for you to write on, and you can do that sometime before the next test. It's real easy. So mirrors, are they, well, they're not rough, they are what? Smooth, and that makes them where they can reflect. Any real smooth surface can be a mirror and can reflect. Now, there's the light that comes into the mirror, and there's the light that bounces off the mirror, and they have two different names. The light coming in is called the incident ray, I-N-C-I-D-E-N-T, the incident ray. The light bouncing off, this one's easy, is called the reflected ray. The reflected light, okay, it's bounced off. So this is the incident light coming into our mirror. This is the reflected light. This angle is called the angle of incidence. This angle is called the angle of reflection. And if you take physics, you get to do math with those angles. But we're not going to do math because we're not physics. We're physical science. We just learn it conceptually. Miss Olivier, we're ready to move on up.
Say a prayer.
Yay! Okay, like right there's good. All right, so if you have concrete that is rough, instead of bouncing off nicely, it bounces off at crazy angles. And that's why you can't see off of concrete. You can't see your reflection on that concrete wall. But you can see your reflection in the glass over there. I see myself waving because it's smooth. So there might be a picture on the test where it would be something about that. Okay, so here, these are our two kinds of mirrors. They're called convex and concave. Convex goes out. Concave goes in like a cave that a bear lives in. If it is convex, the image that you see is right side up. Draw a little pencil here. Y'all can draw better than me. There's a little pencil. So it will be right side up, and the light kind of bounces off the image like that. Okay? And it's right side up. So make a little pencil here that's right side up. If it's concave, the light bounces like this, and it makes the image upside down at this point. Now, we'll do a little lab activity. I really should have drawn that more over here, the image upside down. If you're close enough inside the concave, it'll make it right side up. So draw a right side up pencil real close, and an upside down pencil sort of further away. Those are upside down pencils. Don't those look like pencils? Right side up pencil, upside down pencil. And on your little simulator, it's a pencil also. That's why I drew it as a pencil. You can have mirrors that are concave and convex. You can also have lenses that are convex and concave. Some of y'all have to wear glasses, and you either have convex or concave depending on if you are nearsighted or farsighted. Now you can get light to reflect, and it can reflect all the way back into the medium. That's called total internal reflection, and they use it for fiber optics. Y'all heard of fiber optics? So that's another job you can have. You can work putting like down fiber optic cables. You can work for, Comcast. It's a good job. There's a lot of good careers that you don't have to go to college for. you go to technical school for a lot of good careers that make a lot of money in this stuff. Okay, can you roll it up, Miss Olivier? Moving right along through these notes. Okay, this is explaining to you brightness. Things look brighter when they are close and has a lot of light. Things look dimmer like spray paint when it's further away and more spread out. So all you have to write here is this would be like bright light. And this is like dim light. Dim light comes from a source that's further away, so it's more spread out. Bright light is from a close source where it's not spread out. Okay, next page. We have an eyeball. This is what your eyeball is like. It's round. The back part of it is called the retina. You have a nerve going out the back of your eyeball called the optic nerve. It causes a blind spot. But it's because you have two eyes, you don't see it, and your brain helps get rid of it. But that's that thing where they make you cover an eye at the eye doctor and they move the little thing around. They're looking for your blind spot. They want to see where your optic nerve is. You have a lens. It's not made out of glass, but it's made out of something a lot like it in your eyeball. You have the colored part of your eye, which is called the iris. And the iris can get big and small, changing the size of the hole in your eye, which is called the pupil. That's the black part in the middle. You have a covering to it, the cornea, that protects your eye, and it can get scratched or it could get torn. One time my dad tore his and got his eyeball infected. It was one of the grossest things ever. So if you ever get your eye scratched or whatever, you got to go to the eye doctor. You can't wait. You'll end up losing your eyesight. They will put medicine on it. Don't think it's going to be okay. Anything pokes you in the eye or get chemical in your eye, go to the doctor. Don't mess around with your eyeballs. Your eyes are too precious. Okay, moving right along. You have to be able to label that diagram. So we don't have anything to write there. I gave you all the answers. That was very nice of me. Turn to the next page. Okay, some of you have perfect vision, like my son Eli. So that means the light comes in your eyeball and it focuses on the back of your eye where it's supposed to. Some of you are nearsighted, which means that you can see up close, but you cannot see far away. That's me. I can see close, I can't see far away. So that means if I'm not wearing my contacts or glasses, instead of focusing on the back of my eyeball where it's supposed to, it focuses right in the middle of my eye. Because my eyeball is too elongated. My eyeball, instead of being this nice shape, it's like it's been squished and it's too long lengthwise. How they fix it is they put a lens on it that makes it focus on the back. That looks like this. People who are nearsighted, their glasses or contacts are thicker on the edges than they are in the middle. You ever heard anybody insult somebody saying, oh, they wear Coke bottle glasses? That means they're nearsighted. Coke bottle glasses, okay? The other one is farsighted. That means you can't see close, but you can see far away, like Hawkeye. You all been watching that? It's a very good show. Okay, so with farsighted, their eyeball is too tall. So instead of focusing on the back of the eye where it's supposed to, if it continued, it would focus back here in your brain somewhere. So they put this kind of lens in it that's thicker in the middle, thinner on the edges, and makes it on the very back. I thought that was interesting, and you needed to see that because I bet a lot of y'all are wearing contacts or glasses, and it's interesting to see what's wrong with your eyeball. And some of y'all are rejoicing because you have perfect vision, which is totally not fair. Let me just tell you, it's not fair that some of y'all have perfect eyeballs and I don't. Neither does Miss Olivier. She's got her glasses on. Nearsighted or farsighted?
I have both. I've gotten older, so I have
the bifocal.
I've got something on the top and something on the bottom.
Okay, so what that is, we'll use Miss Olivier. It means that her eyes, that she's nearsighted. Her eyeball looks like this. But how your eye focuses is the muscles make that lens move, and the lens can squish and it can smooth out. It's not like a piece of glass, it's a living lens, and it can get thicker and thinner. But every year you live, your body puts another coating of lens on the lens, and it gets stiffer and stiffer till it doesn't move anymore, and then you have to have bifocals.
That was me.
Yep.
About 10 years ago, I started to not be able to read. I kept holding my book further and further away to read it, and I'm like, I just need glasses.
Yep, that's what it is. So live long enough, it'll probably happen to you too. All right. Now, but because of that, sometimes people who are nearsighted, as they get older, their vision will correct to perfect.
That's funny.
Isn't that funny? So instead of being both like you, they end up where it corrects itself.
Wow.
So that's it gives us hope, those who are nearsighted. All right, next page. That was an easy one, wasn't it?
That was fun.
Okay, we're sideways, but that's all right. We can still look at. Our next one, this is what the transverse waves look like that are light. On the lowest wavelength down there, it's radio. So the longest wavelength is radio. And the shortest is gamma. You know, gamma rays that turns Bruce Banner into the Hulk. Okay. So these little blanks tell you the electromagnetic spectrum. The slowest wave is radio. Not slowest, they all go at the speed of light. The longest one, whoops. The longest one is radio. Then comes microwave.
What's that one called?
Microwave.
Microwave.
Okay, then comes infrared. Oh, it doesn't like that.
What's the first one again?
Radio waves. I'll write them over here.
Yeah.
I'll just write these on the board and you can write them down.
Something happened here.
So it's radio, micro, infrared, that's heat, infrared, visible, that's what you can see, UV, ultraviolet, X-rays, and then gamma rays. Then gamma. So how I remember this, well, a student made this up years ago. Ronald McDonald is very ugly, extra gross. Ronald McDonald is very ugly, extra gross. So that's the whole electromagnetic spectrum. That's all the light. The light we can see visible and all the light we can't see. You know, some animals can see what parts of that we can't see. We can only see the visible. Okay, so notes about radio. Nothing really much about that. But just know that radio waves are light. We think of them as sound. They're not. Your radio turns this light into sound. That's why the DJ can say something in Atlanta and we hear it instantly out here in Dallas, because that what the DJ said traveled to us at the speed of light. Now we can't hear it in this room unless we get a radio, and then we can hear it in the room. Does that make sense to you? In that, the radio turns it into sound waves that are slow, but light waves are super fast. Okay, I wanted you to know about infrared, that it's heat. Infrared is heat, so write that down. I'll write it sideways. You write it right side up. Oh, it's not going to let me.
Hold on, let me see. Let's do.
Okay.
Now see if it'll let you.
Let's see if it'll let me. Yeah. Know that infrared is heat. Okay. I want you to know with ultraviolet that bees can see it. And it also makes you tan. And it can give you cancer.
Ooh.
So when they try to lie to you at the tanning bed and say, oh, these aren't the rays that give you cancer. Yes, they are. They're lying. And you just need to be happy with the color you are and not go to those tanning beds. You need to wear sunscreen. Okay? That was your, let's not get skin cancer. Let's be happy with the color we are talk. It's not worth it. Microwaves, what I want you to tell about that is, of course, it's a microwave oven, but that's also how your phone works. Your phone works on microwaves. So there are some people who think they're not good for you to have it up next to your head, that, you know, having a microwaver up next to your head could give you, like, cancer, some people think. Now, the phone companies say, oh, no, it'll never do that. but it's controversial. Okay, another one, the visible light, that's the rainbow, Roy G. Biv. Now, X-rays and gamma rays, they give you cancer too. They definitely give you some cancer there, X-rays. And that's why they put that big heavy lead thing on you when you go to the dentist and they take your X-ray. They always put that big heavy lead thing on you, the apron, and it comes up around your neck because you really don't want your neck to get cancer in the thyroid. So, all right, so we're through with that page. Okay. That wasn't so bad. Okay, next page is another one to look at. This is a little drawing that explains to you how light can bend, why light bends. And the reason why light can bend is because it's going from one medium to another, and light goes a different speed depending on what it's in. Light travels faster in outer space than it does through air on Earth. It travels faster through air than it does in water. Does that make sense? And when light goes from one thing that's traveling into another, it can turn just like if you ever had a little car, playing with it, and you rolled it across a wood or tile floor onto a carpet, but it doesn't hit even, it hits at an angle. If it hits at an angle, the wheel that hits the carpet first will slow down faster than the wheel that's still on the tile, and it makes it swing around. And it'll change the direction. So here's our wheel, our thing going along. This way, wheel hits the carpet and makes this wheel swing around, and it changes the direction. That's how light changes direction too. Okay, next page. And we'll talk more about that. Okay, so now we're going to talk about color. So color, white light is made of, let's see if it lets me write. Yeah, it does. It's made of all colors put together. So white light is like a compressed rainbow. It's made of all colors. So reflected light is what makes light have colors. And I'll explain that to you. So for example, I have this yellow piece of paper. That means that the light, the white light hits it, and most of the light is absorbed. But the yellow it doesn't like. This pigment doesn't like yellow. It doesn't want the yellow light, so it reflects it back to your eyes so you see yellow. Does that make sense to you? This yellow paper is taking all the colors and keeping it, except the yellow it doesn't like, it reflects it. The green of this lid, it likes all the colors but green, and green it reflects back to your eyeball so you can see the green. Okay? Why does that happen? It's this. The color depends on two things. The light, what color the light is, and it depends on the object, the material. The material it's made out of, how it interacts with the light is why it happens. Okay? Colored light. So that's white light. What about colored light? You ever bought like one of those light bulbs at the grocery store that's like red, tried to make your room all exciting and put a red light in there? Anybody ever done that? Okay, colored light makes things either look dark, they can make things look dark, or the color of the light. And I'll explain that to you. And you've probably seen this before. It makes it either dark or the color of the light. So example, if you shine a red light on a green object, it's going to look dark. But if you shine a red light on a red object, it's going to look red. If it's the same color of the light, it looks like that color. If it's a different color, it looks dark. Has anybody ever seen this before? Now, colored cellophane, we see that this time of year. It is a filter. F-I-L-T-E-R. It's a filter. And it will only let the color it is pass through. It only transmits the color it is. They have fancy ones called gels. If you've ever worked in theater or stage, they have these colors, or been to a concert. They put these little colored filters in front of the light. They're called gels. And like if they put a blue one, it will make a blue beam of light shining down on your rock star so he looks really cool while he sings this song. Y'all know what I'm talking about? You can check it out on YouTube. There's concert footage there. Okay, we're ready to scroll. And I think we're going to stop at the bottom of this page because we had some technical difficulties. We didn't get as far, but we'll finish it tomorrow. And we'll do some labs with this too. But we're going to do the bottom part where it says color spectrum. Can you get to scroll?
This part?
Uh-huh. So this is a prism. Has anybody ever seen those? Played with them in elementary school? It is a glass triangle. And you shine a light into it and it makes a rainbow. I used to have one, and I've taught so long, I've taught on an overhead projector. I know, it's shocking. Yeah, I know I don't look that old. But you can put one of those prisms on the overhead projector and make rainbows. So this is since white light is made of all colors, it can be separated into the rainbow. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Y'all all know that, right? So the prism can separate it into the light. Red gets bent the least. So red, the rainbow is always in this order, and violet gets bent the most. So that's what makes it. Water drops can make a rainbow, and also colored light can be mixed. And that's where we're going to stop. You can mix colored light, and you would also do that if you work in a concert hall or a stage. You can use lights and mix the colors. All right, so this isn't going to be terrible. We'll finish these up tomorrow, and then we'll have an open note test on it on Monday. Like, share, subscribe.